Welcome back to our physics experiment. Today we will be investigating the relationship between force and energy using ramps.
Our main problem was identifying what relationships exist between the energies and forces of an IO lab as it rolls down a ramp at varying angles against the table surface. Our goal was to use the IO lab software and a scale to measure the velocity, acceleration, and mass of the IO lab to calculate how kinetic energy and force relate to work. We hypothesized that gradually increasing the ramp angle that the IO lab rolls down will produce a directly proportional relationship between work, calculated as the change in kinetic energy, and force over distance of the IO lab. Our results showed that a directly proportional trend between both methods of calculating work. In addition, they resemble a near one-to-one ratio.
So in this experiment, we are investigating the work-energy theorem. That is, work equals the change in kinetic energy and the force being applied multiplied by the distance. Therefore, due to the transitive property, the change in kinetic energy is equal to the force applied over the distance. In essence, a force is necessary for a change in velocity to occur.
So this is our system schema for our experiment. We decided to have the IO labs the only thing in the system. The Earth is outside the system and exerting a force of gravity, which is what actually causes the work, and this can be seen by the force arrow crossing the system boundary.
A free body diagram is useful to visualize the forces acting upon the IO lab. Here we can see a normal force, the force of gravity, and a component of the force of gravity in the x direction that pulls the IO lab downward towards the table.
Since the Earth is doing work on the IO lab, there's a change in kinetic energy within the system. The kinetic energy is getting bigger over time as the IO lab approaches the bottom of the ramp as it gains velocity. Additionally, some internal energy is present in the form of sound, friction, and heat. However, it is much smaller in magnitude relative to the kinetic energy of the system. It is important to note that the size of each circle is proportional to the total energy of the system. The total energy increases as the IO lab descends.
For our procedure, we first took the mass of the IO lab, then we set our whiteboard to our set ramp height and held the IO lab at the top of the whiteboard. We then recorded the velocity and acceleration and force of the IO lab from when we released it until it reached the bottom of the ramp. We then repeated this experiment with the whiteboard at different angles. Between each trial, the IO lab device and software, as well as the distance it traveled down the whiteboard, remained consistent.
To use this experimental design to fit our models, we'll be targeting the increasing kinetic energy of the energy pie chart models. This yields the initial and final kinetic energies for the work calculation. We will also be targeting changes in the force of gravity in the x direction for different ramp angles in the free body diagram. Here we'll use the acceleration to calculate force and multiply by the distance to find the work, and then we'll compare these two methods. Initially, we anticipated that friction could alter the force of gravity in the x direction of the IO lab as it rolls down the ramp. This could potentially alter the force and final velocities of the IO lab as it reaches the bottom of the ramp, which could decrease the amount of work done by gravity.
So after conducting the experiment, we compiled our data into two graphs. The first graph shows the relationship between the change in kinetic energy and the force multiplied by the distance. If you look closely, you will notice that the relationship between the two products is almost a perfect one-to-one relationship. This helps support the work-energy theorem stated previously. Additionally, the second graph shows the relationship between the angle of the ramp and the final velocity of the IO lab. The parabolic trend shows that as the angle of the ramp increased, the velocity of the IO lab increased as well.
Possible errors in our experiment included the precision of using the IO lab software. An example of this would be altering the start and stop time of our recordings. This in turn would affect the change in time and subsequently the acceleration and force calculations. Another possible error was the flexing of the whiteboard. This flex on the board would alter the angle of the ramp and not provide a constant force of gravity in the x direction.
The underlying physics in our experiment show that the directly proportional and approximate one-to-one relationship between the change in kinetic energy and force over distance graph supports the work-energy theorem. In order to have a change in velocity, the object must accelerate, and in order for the object to accelerate, a force must be present and acted over a certain distance. In this experiment, gravity acted as the external force which caused the change in velocity, essentially a change in kinetic energy.
In all, we initially hypothesized that as we increase the ramp angle, the final velocity of the IO lab will increase. This means that the change in kinetic energy that occurred was proportional to the greater force experienced by the IO lab as it traveled down the ramp. Our results support this hypothesis by displaying the approximate one-to-one relationship between the change in kinetic energy and the force exerted on the IO lab as the angle of the ramp was increased.